Good day. Welcome to this next video. In this one, we're going to be talking about some of the properties of definite integrals. In the previous couple of lessons, we defined a Riemann sum, basically when we were talking about estimating areas under curves with rectangles. And then we defined that the limit of that process as the definite integral, the exact area or net area under a curve. And then today we're going to talk about some of the properties of definite integrals. Basically some ways that, some properties or ways that integrals work that help us work with and calculate their values sometimes in easier way. Let's get started. The warm-up problem here shows the graphs of two trigonometric functions that you're hopefully familiar with. One is the sine function, y equals sine x. That's this one here. And then the other one is y equals cosine x here. In the last videos, we talked about this definite integral symbol. And for now, we want to interpret that as area. And so, for example, I've given you a value of a definite integral here. I've given you that for this, on this sine curve, the definite integral measured between 0 to pi is 2. So if I go over here and look at my picture, that would mean that if I were to shade in with my highlighter the interval from 0 to pi, that the area is 2. Okay, so you wouldn't have known that ahead of time. Okay, but this I'm just telling that to you. So the area of there is 2. So what you're asked to predict is what would be the value of the definite integral from negative pi to 0. Sorry, negative pi to pi. So that's to go all the way across. Okay, so now I'm going to shade in all the way from negative pi to 0, and then we're also going to have to include this one. What do you think the total value of this integral is? And let you think about that for a minute while I talk about the other one. In the second instance, the given information is that the integral from 0 to pi over 2 of the cosine function, that would be this region here, this one has an area of 1. Okay, so let's actually talk about the first one. If the definite integral 0 to pi, in other words, the region here has a value of 2, what would be the value if I go in from all the way from negative pi to pi? Well, my first thought is we know that the graph of sine x has symmetry. In other words, this is an exact copy. This bump down here is an exact copy of the one up here, just it's drawn underneath. So it makes sense that this has an area of 2 also. But is the value of this integral really 4? And in the last couple of lessons, we kind of came across the discovery that when the function is below the x-axis, the integral value is going to be negative. And so even though this has an area of 2, the integral value is actually going to be minus 2. And now it makes sense that if I'm going to go all the way from negative pi to pi, that I actually have to add those two amounts, and so my actual value is 0. Okay, so essentially if my integral value is 0, there's either no area at all, or the sum total of all the areas is 0, because some of them are negative and some of them are positive. And that's what's happening on this one. We're demonstrating really one of the properties of definite integrals that we're going to list in a minute here, in that I was able to add the area here to the area here to get the combined area from negative pi to pi. Okay, here's another one here. We know the cosine function has symmetry also. This time it's exact reflection across the y-axis. So it would not be surprising at all if you predicted that the area that I'm going to shade in now is also 1. And so now if I wanted to find the integral value from negative pi over 2 to pi over 2, it would make sense that we would just add these together, and the answer is 2, and that is actually correct. So based on the same reasoning as above, the integral is 2 because I was able to add those two separate values together. So this leads to our first property of integrals, which is what I call the interval addition rule. See, I was able to add two adjacent integral values to make a bigger one. And see, so this picture shows that general principle that I have the interval a to b broken up into two parts by going from a to c first, then from c to b. Now, they've drawn it so that c looks like it's about halfway. It does not need to be halfway. Right? C could be anywhere between a and b, and this works. So the given here is that a is smaller than c, and that c is smaller than b, and that f is continuous. On this interval AB, like it is in this picture here. Okay, so now the idea is if I were to take the definite integral value from a to c, which would just be this guy right here, I'll write it red for a minute. And then take the integral value from c to b, adding those together because they're just adjacent to another here, they overlap here at c. If I just add those together, that would be the same thing as me asking what's the area all the way from a to b, which would be the integral from a to b. So we get this little integral addition statement here. The definite integral from a to c plus the definite integral from c to b would add together to be the same answer as if I had the definite integral from a to b. It makes just perfect sense that we're just adding adjacent areas to one another. So as long as there's that common number c, we can just add this across here. Okay, two other properties that we're going to use today, and that is, this one says if my function f of x is then multiplied by another number k, or a constant. If you think about it, if I asked you to graph y equals f of x and then asked you to graph y equals 2 times f of x, it just doubles the height of everything, right? Or multiplies the heights by whatever number this is. So if you think about going back to our Riemann sums and our rectangular sums, that would make all the rectangles k times bigger, taller, which means their areas will be that many times bigger. And so essentially what this is saying is I can kind of bring the constant out if I wanted and find the value of the integral of f of x. If I happen to know that, it's easier to do, and then just multiply the answer at the end. Okay, so for example, remember the problem in the warm-up today? If I changed it to the integral 0 to pi of 4 sine x, I could then rewrite it as 4 times the integral from 0 to pi of just sine x. And so that would allow me to use the given. Remember I told you that the given integral 0 to pi of sine x was equal to 2. And so therefore I would just know that the answer to this new integral is going to be 8 because I would just be able to multiply the old integral by 4. Right? Okay, this one is, what if two functions are added together and then we want to take their integral value? And this is basically saying that integrals can be split by addition, and saying I can instead find the integral of f of x and then find the integral of g of x on the same interval, still be a to b on both. And then if the two functions are adding, we'll be adding, and if the two functions were subtracting, we'll be subtracting. Okay, so we're actually going to use those properties now to evaluate an integral that you would not know how to solve otherwise, because if I were to draw the function negative x squared plus 4x minus 3, that's going to draw a parabola, and so the exact value of this integral would be difficult to get exactly right now. But what I'm going to do is I'm going to give you 3 integral values that you can just use as your helpers in this one. I'm going to give you 3 integral values over here in the upper right corner. The function x squared from 1 to 3, I'm just going to give you that one. I know the exact area under the curve on that interval is exactly 26 thirds, which is like 8 2/3. The graph y equals x on the interval 1 to 3. It turns out the area is 4, the integral value is 4. And the function f of x equals 1 from 1 to 3 also is 2. So I'm going to demonstrate how I would solve this integral using those givens right there. The first one is I would split this into 3 separate integrals using that addition property of the last slide by writing this as the integral of negative x squared from 1 to 3 plus the integral of 4x also from 1 to 3, and then minus the integral of 3 from 1 to 3. But now, none of these integrals are exactly the ones in the givens, but they can be made into them if I remove the constants from each of the integrands or the expressions. So this first one has a minus 1 coefficient, so I can factor negative 1 out as the constant using that constant rule. I can factor out 4 from this one using the constant rule. And I can factor 3 and just call this 3 times 1, so I can write 3 here and still keep the 1 in here. So you see now how the given integral expressions now are the exact ones that are appearing in here. And they're just each being multiplied by their appropriate coefficient. So I'm just going to take this answer now, the final answer that I'm not going to compute, but I'm going to write it out a little bit here, would be what I would get by taking the negative of 26 thirds plus 4 times 4, the given integral up there, and then 3 times 2. So if you take your calculator or whatever you want to do and add that together, that's going to give you the grand total. I encourage you to pause the video here and try to do that same approach with the second one, and I will write it out for you so you can look at it in a minute here. Okay, I went ahead and wrote out the solution to the second one. Now I did the first 2 steps in one line this time. I separated into 3 integrals, and I also factored out the coefficients 2, negative 1, and 7, leaving me with the 3 given definite integrals. And I was able to pull the answers to those from up here. So my final total will be, what if I were to add together 26 thirds times 2 minus 1 times 4 and plus 7 times 2. If I added all that together, that's going to give me the grand total there. Okay, 2 other properties to mention. This one's kind of curious. It's the definite integral of f of x dx, but I've made the same number at both ends here, a to a. So if I think about that, normally we think of the integral as being from a to b, some other b out here, and I draw the function and measure the area. But this time it says just from a to a, which means I'm not going to be able to move off of this spot. Okay, and so in that case, I really don't have a delta x to even draw a single little rectangle there. Okay, so because of that, it makes sense, hopefully to you, that this integral, if it's ever from a to a, like 1 to 1 or 2 to 2 or 0 to 0, any one of those, the integral value should be 0, simply because we haven't traveled anywhere along the curve at all and haven't been able to accumulate any area there. Okay. This other one is a little curious too. Notice this one, I've got the standard integral a to b, f of x dx. But on the other one, I have reversed what I call the limits of the integral, b and a. So if I go back to my picture now and picture, the drawing would be the same for both, wouldn't it? Because the a and the b haven't changed. And the definite integral, if you think of it as the area. So I put a question mark there. Do you think these integral values are the same? Like, for example, like if I put this as the integral from 1 to 3, is that the same as the integral 3 to 1? And I'm just going to make the function y equals x to make it easier, just to make a simple one. Do you think those integrals are the same value? Turns out they're not, and the reason why is because if you go back to the definition of a definite integral, remember that Riemann sum, the rectangle sum? I'm going to write it, I'm going to remind you of it here. And then the limit of that is the definite integral, right? But back in the definition of a definite integral is this Riemann sum. If I reverse the limits of the integral, instead of being from 1 to 3, where the lower limit is the bottom and the upper limit is the top, that would mean we're going from left to right. If I change it 3 to 1, it implies we're going from right to left. And what that would do to the Riemann sum is it's going to affect this delta x in the Riemann sum. Because now, even though the function values might be positive, the delta x, if I'm moving from right to left, is going to be negative. And so now the product of the height times the width is going to be negative, or it's going to at least be the opposite sign because the delta x is now going to be negative. So what has to happen here is for this equation to be true, and I'll just go ahead now and erase the question mark. Okay. In order for this equation to be true, we need to put an opposite sign on one of these integrals. Okay, so in this one too, by switching the limits of the integral, the sign value is opposite. So if the original integral going left to right was a positive value, if I integrate going from right to left, it's going to be negative. Okay, so this will demonstrate those two properties real quick here. If I take the sine of x from 2 pi to 2 pi, since the lower limit and upper limit are the same, this is automatically 0. For the second one, I'm going to draw a picture of this. It's the function f of x equals x plus 3 from 0 to 3. Okay, so then my graph would go 0, 3, and slope up by 1s. So by the time I get to x equals 3, this is the point 3, 6. Here's my line, and here's my region. So now the integral still represents in one way the area. And so let's divide this up into a rectangle and a triangle again. This is going to be a 3 by 3. It's actually a square, so the area will be 9. And this one is going to be a 3 by 3 triangle, so it's going to have an area of 4.5. So the area of this region is actually 13.5. But is the integral 13.5? Well, it's the thing that was different here was this was the integral 3 to 0, which is actually starting at 3 going to the left. So that last property of integral says I should actually write this again, but go 0 to 3 and just change the sign. Okay, so the actual area 13.5 is what the value of this integral is without the negative sign. So now that I have a negative sign, this original integral has a value of negative 13.5. Okay, because I switched the limits of the integral back to the regular order, 0 to 3. So I'm looking at the picture from left to right. But then by switching those limits, the integral changes signs, and now the actual value of that integral originally is now going to be negative 13.5. I hope this all helps you, and we'll see you back in person in a couple of days, and we'll finish off this lesson. See you back in a couple of days.